Hello friends, last lecture I discussed about the history of organic electronics and organic materials. Okay, now I am going to discuss about the organic optoelectronic devices and the optoelectronic devices. Right? So organic materials and any kind of the materials, if you think about the any kind of the materials, any kind of the materials show electrical, optical and mechanical properties, right? So based on the electrical, optical and mechanical properties, we can design different kind of the devices, right? So here, if you want to design the any kind of the devices like optoelectronic devices, this is based on the electrical and optical properties. And optomechanic devices, the reverse way, like electro-optical devices, mechanical and optical devices, electrical devices, electronic devices, right? Now, for case of the organic materials, right? For case of the organic materials, right? So organic materials, we can use organic materials in electrical devices, electronic devices, mechanical devices and electronic devices, right? So electrical devices, electronic devices, electro optic or optoelectronic devices, mechanical devices and so on, right? So here, in case of the organic materials show extraordinary optical properties as compared to the electrical properties. One of the optical properties is that is strong optical absorption coefficient, right? Organic materials have strong optical absorption coefficients. Due to this property, we can use the organic materials in case of the optoelectronic devices. So if you design organic optoelectronic devices by employing organic materials, so it will be more superior as compared to the electronic devices. Okay, so what is the organic optoelectronics? Before discussing the organic optoelectronic devices, first we have to know about the optoelectronic devices, right? So we will discuss about the electronic devices which can be designed by the organic materials. That will be later. Okay. Right. So that organic optoelectronic devices, that will discuss later. First we should know about the optoelectronic devices. Okay. So why I am considering the optoelectronic devices that I discussed just now, because uh, organic materials show extraordinary optical properties as compared to the electrical properties, right? So optoelectronic devices. So there are multiple optoelectronic devices like light emitting source, photodetector, optical modulator, optical fiber, optical transistor or phototransistor, and filter, so on, right? So in this all the devices, photon plays important role in order to design the organic optoelectronic devices or optoelectronic devices, right? Because the photon plays vital role if we design the organic optoelectronic devices which can be used in the IT and the optical computing applications due to their high bandwidth and the privacy issue. Okay, now here, and a light emitting source, photodetector, and light emitting source, photodetector, and optical fiber. These three are the main components if you want to design the optical communication system. And other components are also important, right? But if you want to design the optical communication system, that means if you want to send any information in the form of the optical from transmitter to receiver, the optical communication system is mandatory, right? So light emitting source, photodetector, and the optical fibers, these are the main important if you want to design any optical communication system or optoelectronic systems, right? And the other parts are different: optical modulator, optical filter, then phototransistors. These are important if you design an integrated circuit, optoelectronic based integrated circuits, right? So first I'll discuss about the light emitting source. Light emitting source. Right? Light emitting source, that means it is a device, okay, which is used to convert the light energy into the optical energy, right? So definition of the light emitting source: it is a device which is used to convert light energy to the optical energy. Okay, how can you design the light emitting source? It is like it is one kind of the diode, PN junction diode. Okay, PN junction diode. So it made up of PN junction diode, right? And it is operating by forward bias, right? These two features are required. It should be made up of the PN junction diode and it should be controlled by the forward bias. Okay, now PN junction diode means it is one kind of the device which consists of P type semiconductor and the N type semiconductor. If you connect two P and N type semiconductors together, that will become PN junction diode, right? So here I'll discuss about the working principle of the light emitting source now. So here, this is the band diagram of the PN junction diode. This P-type band diagram of the P-type semiconductor and N-type semiconductor, right? So now you can see there is a band at the interface of the PN junction diode. Why it is happening? So when you connect the P-type semiconductor with the N-type semiconductor, right? Okay, this is called the after contact. Okay, before contact, the P and N-type both two are the different semiconductors. So after contact, so this will become a one kind of the device, PN junction diode. Okay, now to maintain the Fermi level of the PN junction, there is a band at the interface of the PN junction diode. This Fermi level should be at the same level. Okay, because in case of the P-type semiconductor, the Fermi level is near to the valence band, and in case of the N-type semiconductor, Fermi level is near to the conduction band. But to maintain the thermal equivalent condition, this Fermi level should be at the same level. That's why there is a band at the interface of the PN junction diode. Now you can see there is an energetic barrier that is called the delta EC and the delta E suffix B. Energetic barrier at the conduction band and energetic barrier at the valence band. Okay, Now what will happen? Now here we will apply the forward bias. That means this terminal is called the anode terminal. So this is the one kind of the metal contact. There is one kind of the metal contact. There is another kind of the cathode contact. Okay. Now forward bias means if we apply the positive voltage at the anode side and the negative voltage at the cathode side. So this is means this is under the forward bias. Okay. Now here you can see if we apply the forward voltage here at the cathode terminal, positive voltage at the cathode terminal and negative voltage at the forward voltage at the anode terminal and negative voltage at the cathode terminal. Okay. Now in case of the p-type semiconductor, holes are majority, and in case of the n-type semiconductor, electrons are majority. Okay. So if we apply the negative voltage, these electrons, whatever electrons are there inside the valence band, okay, this repelled away from this junction, okay, and these electrons try to move towards the p-type semiconductor, okay, and whatever holes are present inside the p-type semiconductor, these holes are repelled away from that junction and try to move towards the n-type valence band of the n-type semiconductor. But as there is a energetic band gap at the conduction band and the valence band at the interface of the conduction band, okay, so this electron will not move freely towards the p-type semiconductor, okay, in the same way the holes cannot move freely towards the valence band of the n-type semiconductor. So there is a confinement of the electron and the hole at the interface of the PN junction diode. Okay. Now at that moment electrons fall down from the valence band to conduction band. Okay, electrons fall down from the conduction band to valence band and emit a photon. Okay, that means we are getting the optical energy from the device. Okay, so there is a emission of the photon. Okay, so energy of the optical energy of this photon, that is E optical. Okay, that is equal to the energetic difference between valence band and the conduction band. Okay, EC minus EV, energetic difference between valence band and the conduction band. This that is already that you can represent by h nu or h c by lambda. What is the nu? Nu is the optical frequency and lambda is the this emitted photon. Okay, we are getting the emitted photon, the wavelength of the emitted photon, that is defined by the lambda, hc by lambda, right? So the energetic gap between the valence band and conduction band, that should be similar to the optical energy. Okay. Now coming to the types of the emission. So there is a two different kinds of the emissions, that is a spontaneous emission and the stimulated emission. Okay, so based on the emission types of the emission, there are the two kinds of devices, light emitting sources. One is the light emitting diode, another is the laser diode. Okay, light emitting diode and laser diode. Okay, so this is related to stimulated emission. This is related to spontaneous emission. Stimulated means at the same time we can get multiple numbers of photon in case of the stimulated emission. Okay, so this is mainly laser diode is mainly used for high power application. If you want to produce a high power, so for this, that case we can use the laser diode. And light emitting source, that is mainly used in the optical as a transmitter in the optical communication system, right? Now I am going to discuss about the types of the light emitting diode, that is based on the types of the structure. Okay, homojunction, heterojunction. In case of the heterojunction, single heterojunction and the double heterojunction. Homojunction means in this case we can use the only one semiconductor, but different doping concentrations are different. Two different kind of the materials we can use in a one semiconductor. Doping rate and doping concentrations are different in case of the homojunction. So if we use the homojunction, we will get less response or less performance. So in order to get the high performance, we have to use the heterojunction. It may be a single heterojunction or it may be the double heterojunction, right? So now I will discuss about the double heterojunction. Double heterojunction. Here I am just drawing the structure of the double heterojunction. Okay. So in case double heterojunction means two interfaces are there, right? In case of the single heterojunction, only one interface is there. So this is the one interface, this is the another interface. So N-type aluminum gallium arsenide, P-type gallium arsenide, and the P-type aluminum gallium arsenides. These are the semiconductors, right? Compound semiconductors. N-type means these N-type impurities are doped inside the aluminum gallium arsenide, which is highly concentrated, and the P-type gallium arsenide and P-type aluminum gallium arsenide. The width of the this layer, gallium arsenide layer, this should be narrow as compared to the other layers, right? So how it will affect on the performance of the device? Here the band diagram. Okay, the N-type. Now we can also apply the here. So this I have to apply the forward bias voltage. Okay, the N-type semiconductor we have to apply the negative voltage, and the P-type semiconductor we have to apply the positive voltage, right? So now we can see this is the N-type and this is the P-type, right? Here it is cathode, here it is anode. Okay. Now here if we apply the negative voltage in the same way, the electrons, okay, this will repelled away from the cathode terminal and move towards the P-type gallium arsenide. Okay, here all the electrons are accumulated. Okay, and in case of the, so here you can say this is the delta EC and the delta EC1, you can define delta EC2, delta EV1 and delta EV2. So this energy, there is an energetic gap, that is the delta EC1, that is the less as compared to the delta EC2. Okay, so electrons that can repel away from the cathode terminal and move and transport easily towards the P-type gallium arsenide. right? And in the same way, the holes are repelled away from the anode terminal and transport towards the p-type gallium arsenide. Okay. Now, as there is a large energetic gap at the p-type semiconductor, at the interface of the p-type gallium arsenide and the aluminum gallium arsenide, so this electron cannot move, cannot cross this barrier. Okay, cannot cross this barrier. Okay. So that times all the whatever electrons are presented at the p-type semiconductor, gallium arsenide semiconductor, these electrons fall down and recombined with the hole. This will produce the emission, photon emission. Okay, so whatever electrons are collected from the cathode terminal, all the electrons are recombined in the hole in case of the double heterojunction. But in case of the single heterojunction and homo heterojunction, we cannot get all the emissions or all the photons. But in this case, we can get the maximum amount of maximum numbers of photons, right? So that means in this case we are getting the high efficiency. Efficiency means, so if you want to define the performance of the device by calculating the efficiency, we can define the performance of the device. What is the definition of the efficiency in case of the light emitting source? Efficiency, external quantum efficiency, right? So it is the ratio. So ratio means ratio between electrical energy to the optical energy into 100%, right? So IB into P by P optical by IB. IB is the current and the voltage, okay, into 100%. So the efficiency that is divided into two parts, right? Optical recombination efficiency and the extraction efficiency of emitted photon. So in some kind of the semiconductors, we cannot get the so whatever photons we are getting after recombination, we cannot get all the photons in the form of the emission. So that means the external quantum efficiency that is divided into the two parts. One is the recombination efficiency, another is the extraction efficiency of emitted photon, right? So if we get the high efficiency, that device will show the good performance, right? So apart from the aluminum gallium arsenide, we can use the different kind of the compound semiconductors, gallium nitride, gallium phosphide, and so on. So based on the band gap of the semiconductors, so the light emitting source will emit the different kind of the lights, like yellow light, green light, and blue lights, and orange light, so on, right? This is about the light emitting source. Not only the light emitting source, that is only designed by the inorganic semiconductors. In the coming lectures, I will discuss about the other optical devices like photodetector, optical fiber, and the optical transistors, and the organic light emitting source, organic photodetector, so on. Okay, thank you, and I will discuss on the organic optoelectronic device on the next lecture.